Good morning. This is your host, Lance Gordon, author of The Philosophy of the Ananke, and this is part 10. We'll continue the reading where we were. The progression of life. From sedimentary rock, radioactive dating, and fossil information, the following evolution of life has been determined. Major sedimentary layer number 1, the Precambrian era, older than 570 million years ago. One-celled organisms are found, invertebrates appear on the scene, primitive marine plant impressions are discovered. Major sedimentary layer number 2, the Paleozoic era, 225 million to 570 million years ago. Marine plants still are evident, invertebrates are still around, fish appear in the rock layers, and land plants begin to emerge. Major sedimentary layer number 3, the Mesozoic era, 65 to 225 million years ago. Dinosaurs and reptilian bones are found in abundance. Birds appear for the first time. Dinosaurs suddenly become extinct in the last part of the era. Major sedimentary layer number 4, the Cenozoic era, up to 65 million years ago. Flowering plants and mammals appear. Grass becomes abundant, and starting in a layer of earth that was dated at about 1 million years old, man-like bones are found. Thus, there is now abundant evidence that not only has the earth changed, but the creatures and plant life have changed as well. All is necessarily in a state of change and readjustment. Later in the book we'll understand why. Lunar rocks. Is there any evidence that the geologic forces of Earth apply themselves in the same manner elsewhere? Is Ananke independent of space? Let us examine the moon for possible answers. The moon is approximately 230,000 miles away from Earth. That is a long way for the forces to travel. Maybe the forces of Ananke only apply to Earth. Maybe we are unique in the universe. Perhaps the universe is divided into regions of influence where different laws of physics apply. This could be the case. The universe could be divided. It could be, quote, not one. It could be 2 or 3 or 100 orders of things. Certainly the odds of it being a oneness are quite remote. It could have partitioned itself into hundreds of independent regions separated by the vastness of empty space. Certainly the regions would never touch each other. Each region could have different scientific laws that would do whatever the scientific laws would do. This appears not to be the case. Stars are basically round and not square or triangular or of the form of a lightning bolt. Galaxies have formed all over the universe. Stars tend to cluster. The universe appears to be one. Interestingly enough, the lunar rocks reveal similar geologic processes at work. Crystalline rocks, brushes, and soil have been found. The rocks contain calcium-rich plagioclasts, pyroxene, olivine, ilmenite, titanium, and iron. Lava flow is suggested from these samples as well as a slow cooling process. Moreover, erosion takes place as indicated by a rounded surface on some rocks on their upper side. Their lower side, that side embedded in the lunar soil, remains jagged. Lunar erosion is accomplished by numerous methods. These methods include temperature changes, meteoric impact, cosmic radiation, and a tidal force, the influence of the Earth on the moon, and even frost action when igneous activity occurs. All these mechanisms work in conjunction with lunar gravity in order to maintain the round shape that we see. Thus, the geologic forces behave in a similar manner at least 230,000 miles away. Dynamic equilibrium on the Sun. The Sun is a medium-sized star. It is a self-luminous ball of relatively dense gas. It is 90 million miles from Earth. Does an Ananke's formula apply there as well? Yes, as you will see soon, it does. The Sun is composed of 66 elements, most of which are hydrogen and helium. They compose 99.03% of its mass. The Sun's energy is generated by a carbon cycle in which carbon is used as a catalyst to combine hydrogen in order to form helium. The byproduct of this fusion process is energy. Essentially, the sun is burning 4 million tons of hydrogen per second, thereby producing energy and the ash, helium. Calculations suggest that the sun can continue this process for 30 billion years. But why doesn't the sun blow up? How can it burn at a relatively constant rate? How can it maintain this state of dynamic equilibrium? The answer is amazingly simple and further verifies the universality of scientific law. The speed of the atomic reactions depend upon the ambient temperature of the sun. This is usually several million degrees. As the process continues, the temperature rises. If the temperature rises, the gaseous ball called the sun expands. This expansion cools the sun and reduces the rate of the nuclear fusion. This explains why the sun does not blow up. But if it cools itself, shouldn't it extinguish itself eventually? Let us continue with the story. The sun cools itself, the reactions slow down, but the gases start compressing themselves as well. This in turn produces heat, which raises the temperature, which increases the nuclear reactions. Thus, the universal forces tend to keep the sun burning in an orderly manner. The sun essentially pulsates like the beating of a heart. The sun does not explode, nor does the flame die. Dynamic equilibrium is maintained by virtue of the opposing forces which operate on the ever-changing sun in a most efficient manner. This is still the formula of Ananke. It is real, 90 million miles away. Ananke and biology. Biology is concerned with the study of life. But what is life? This is not an easy question to answer. Must the object move? Most objects move, such as the earth and meteors. Must the object make sounds? The earth makes sounds when a volcano erupts. Must it have legs? Plants do not have legs, and yet they are alive. So the answer to this question must necessarily be another question. In essence, what are the properties of organisms and plants that make us say that they are alive? What attributes distinguish life from death? The fundamental unit of life, the cell. In 1665, through the use of magnifying lenses, Robert Hooke presented his investigations on the texture of cork, a once living animal. He recognized that living matter was not composed of randomly organized structures. Instead, he found the contrary, that some life was composed of highly structured units called cells. In the 19th century, Schleiden and Schwann published their experimental findings. They concluded, through abundant evidence, that all living things were composed of cells, that these cells were ordered structures capable of reproduction. So living systems can be viewed as an organized collection of other living units called cells, these cells having the fundamental characteristics of growth, maintenance, reproduction, and lifespan. In other words, cells are equilibrium units, and a living organism is the coordinated grouping of these units. In essence, complicated life is merely a larger system of dynamic equilibrium, which is composed of smaller units of living objects. Amazingly enough, the ordered cell has numerous complicated functions. It transforms energy into work. It transforms unrelated bits of matter into an orderly internal structure. It allows its structure to grow and repair itself. It obtains macromolecules from its environment, converts them into energy and the building blocks of matter, and then it eliminates the waste. The physiological purpose of the cell's life is fundamental. That is to say, this orderly process creates structural growth, structural repair, and the eventual reproduction of similar traits. The chemical origin of life. We now understand that all life is composed of cells, that cells are alive and have similar attributes to the creature which possesses them. All life grows, metabolizes food, repairs itself, reproduces, and dies after a given period of time. If we could understand the nature of a cell, then perhaps we could understand its origin. In essence, the origin of a cell is the origin of life. Chemists have traditionally divided matter into two substances, inorganic and organic compounds. Organic molecules contain the element carbon, while inorganic does not. Life is formed from both. It has been found that living organisms are primarily made up of water, an inorganic compound. The chemistry of life is water-based. This may indicate an origin connected in some way with an environment that was primarily water. In addition to water, the carbon atom is critical. Life needs carbon molecules for structure and energy. From carbon and water, the energy substance of life, carbohydrates, can be formed. Include nitrogen and protein can be created. Add a little phosphorus and you get lipids, a form of fat. Fat is not necessary for the original life, but it does appear in later, more complex forms. Therefore, life can be formed by simply rearranging the atoms of carbon, hydrogen, oxygen, and nitrogen. The unique configurations and resulting unique shapes can produce an infinite variety of creatures. This can be accomplished in a similar manner to the 2,000 or more minerals that exist on Earth. If we recall, these minerals were mere rearrangements of the fundamental elements, which in turn were rearrangements of neutrons, protons, and electrons. But how could they form from the primitive Earth of 2 billion BC? Perhaps an answer lies in the primitive atmosphere of yesteryear. Scientists have deduced that the primal atmosphere was mostly composed of ammonia, water vapor, and methane. Methane is a simple organic compound composed of 1 carbon and 4 hydrogen atoms. Thus, the ancient Earth had large quantities of organic compounds long before any organisms appeared on the scene. Due to the primordial rains during the initial cooling phase, many of the atmospheric compounds, along with mineral runoff, entered the oceans. Do these elements naturally mix and form the basic building blocks of life? Do amino acids form by the chance motion of its components? No, they don't. Some other ingredient was necessary in order to make the reaction occur, but what was this missing something? In 1953, Stanley L. Miller performed a vital experiment in order to determine if amino acids could have formed from the initial atmosphere. He set up 2 airtight containers which held the 4 primary gases of ammonia, water vapor, methane, and hydrogen. Both containers circulated the gas, but in only one did he introduce electric energy. After 1 week, he examined the results. The non-energized apparatus contained no complex compounds, no amino acids, nothing but gas. The energized apparatus contained amino acids, urea, hydrogen cyanide, acetic acid, and lactic acid. The conclusion was obvious. The basis of single-celled life was formed in the laboratory. It demonstrated these elements could have been formed in the beginning. These complex organic compounds could have accumulated in the ancient seas over millions of years. All it needed was lightning, cosmic radiation, or the like. It should be mentioned that no such mixture could occur today, since organisms and free oxygen breaks down these compounds very rapidly. Remember, billions of years ago, there were no organisms or free oxygen. It has been found that given enough time, the oceanic soup of complex organic compounds form a more complex macromolecules such as polypeptides and nucleic acids. Perhaps shallow ponds or lagoons evaporated to a point where the amino acids came close enough together in order to form these compounds. In any case, the oceans of the early Earth contained salts, organic molecules, and the like. They were formed by energy being introduced into the primal atmosphere and by the help of the cohesive forces of the universe. If the bonding forces of gravity and the like did not exist, then life could not have formed. Let us continue with the story. From this oceanic hot soup, composed of colloidal protein molecules, a strange thing can occur. These molecules have a tendency to clump together and form what's called coacervate droplets. These droplets have a definite demarcation between itself and the environment. It has been found that these objects have a tendency to absorb and incorporate substances from the surrounding liquid. Some droplets tend to be highly selective, while others will absorb anything. Once inside, the substances are subject to the enclosed environment of the droplet. This allows chemical reactions to take place more easily since they are in close proximity. Surprisingly, internal orderliness occurs among the molecules that are being rearranged. These droplets essentially convert matter into its own internal structure. In essence, it grows. Not only do these droplets grow, but they tend to fracture easily at some diameter. The two fragmented coacervate droplets retain their common makeup. Surface tension heals, quote-unquote, the wound, and two droplets are formed where one once stood. Primitive reproduction and quasi-genetic transfer is achieved. Although these droplets are not considered life, they are only a small evolutionary step away from single-celled creatures. Those droplets that were more successful at dividing and growing survived. Other droplets became extinct. Since the offspring were basically composed of the chemical structure of its parentage, the successful survival traits were passed on. Through a process of variation in the chemical structure of the offspring and environmental favoritism, the first living cells evolved. Therefore, the controlled variation of the droplets, along with natural selection, produced a dynamic equilibrium condition called life. Equilibrium particles form other equilibrium systems that adapt to the ever-changing world in a most efficient way. The end result is a species that stays in dynamic balance with the changing environment. This is the pattern of the Ananke. Darwin's theory. In the preceding section, we touched upon a mechanism that could possibly result in life. This same mechanism can allow life to vary with the proper changing of the conditions in the environment. It is therefore worthy of our time to understand this process in greater detail. This process is Darwin's theory. Essentially, the mechanism is based on two concepts: variation in a species and natural selection. It should be obvious that physiological change in the offspring of any parent is a natural occurrence. We all look different. Some see better, some hear better, some are naturally stronger, some are inclined to be smarter. Variation is inevitable. Fossil evidence suggests that variation has always occurred. In a given sedimentary layer, many sizes and shapes of the same species are found. However, different layers may show enormous differences between what appear to be the same species. What happened? How did the species change? If we take the case of a horse breeder, we notice that he selects the strongest or fastest horses to breed. By constantly favoring a given attribute, he can significantly change the nature of the reproduced organism. The new horses will eventually be stronger or faster than their ancestors. If the genetic structure allows it, then crossbreeding becomes possible. Horses can mate with donkeys to form, for example, mules. Man can create tangerines, or the numerous rose varieties that exist today. So selecting or favoring a portion of the offspring of a given species will necessarily create new forms of life. Artificially, the species could be made to evolve in a short period of time. Thus, the mechanism of selection, combined with the variation that will occur in any species, can produce evolutionary change. But what does the selecting in nature, and how does it operate with the intervention of a selector? Given enough time, the environment selects the attributes that will be passed on. The evidence suggests that in general, the population of some species, like frogs, have remained constant over a good period of time. Yet each mother frog produces hordes of eggs. Only some reach maturity and reproduce. The frog traits that allowed the frog to survive are passed on. Sure, the frog could have been lucky, but in general, the frogs that perhaps jumped higher or reacted faster survived. Thus, variation in the species along with environmental selection can account for a great deal of the evolutionary change that we see in fossils of the sedimentary rocks. In conclusion, we can now comprehend the evolution of life from the original coacervate droplets. These droplets divided and multiplied. Their offspring were similar but varied in trait enhancements. Fortuitous combination of chemical reactions in one droplet may have produced an increased likelihood to survive. This trait was passed on. Other droplets, quote-unquote, died before dividing. In this manner, the first living cells emerged. Variations among the living cells would have been inevitable. Some would have unique traits. Others may have been dual in structure. That is to say, it would appear as if it were made up of two cells that had specialty functions within the organism. Evolution could continue. As the environment changed, it might have favored dual-celled creatures. The dual-celled creatures varied their offspring between single, dual, and three-celled animals. The environment could have favored the three-celled creatures, who in turn produced five-celled creatures and sometimes. Eventually, 100-celled creatures of various survival traits could have evolved. Given this process and enough time, all creatures could have emerged, including man, or so the theory says. So, species diversification, with the help of the cohesive forces of the universe, and natural selection, which is another force, can produce complicated and diverse systems of dynamic balance. That is to say, life is an equilibrium mechanism that seeks balance with its environment toward the physiological purpose of survival. In the ancient past, life forms changed in accordance with the ever-changing world. The world, by its changing nature, allowed other life forms to occur. When the conditions were right, man was allowed to walk the earth. Ananke in mathematics. What is mathematics? Why does it exist? Are mathematical relationships natural in the universe? Does the universe obey mathematical law? Can the techniques of math be used to decode the Ananke? The origin of sophisticated mathematics can be dated as far back as ancient Egypt. Necessity was the mother of this form of mental expression and logic. The Pythagorean theorem of solid geometry was used by the Egyptians. They discovered it independent of the Greeks, out of necessity. The law was simple. The sum of the squares of the legs of a right triangle were equal to the square of the hypotenuse. Their great architectural achievements were based on the knowledge of the underlying principles of orderly structure. Mathematics helped improve the lives of men. By using mathematics, man did not have to think that hard. All they had to do was describe the problem in mathematical terms, manipulate the formulas in an algorithmic fashion, and interpret/verify the mathematical results. It was a computer in disguise. But why did it work? By chance alone, this should not be the case. The answer is intriguing. Orderly structures or repetitive patterns look different from pure chaos. It turns out they look different due to the orderly arrangements between its parts. These orderly relationships almost mystically can be described precisely by mathematics. The whole object may not be describable by a single formula, but numerous equations may describe 90% of what we see and feel about the object under scrutiny. This is absolutely unbelievable. Pure order can be described by mathematics. From this observation, it was speculated that the ultimate laws of the universe can be described by mathematical formula. Reality is merely a combination of the struggle between this perfect law and pure chaos. Under this assumption, observations of natural events should be describable by smooth mathematical functions and the inevitable error that surrounds these best-fit curves. Indeed, science has found this to be the case. Formulas are only approximations to reality. Orderly distributions, which contain some error, are more real and in abundance. Since reality is the conflict between the pure guiding law and chaos, it would be useful to talk in terms of mathematical tendency. The outcome of events only tend to go a certain way. Most electrons go from the negative to the positively charged plate. A small percentage diverge from the predictable path. Most atoms bond under this set of circumstances. Some do not. No reaction in this universe is absolutely free from error. Chaos is only bound by law. It's not dictated by it. So mathematics had to deal with this imprecise behavior. It had to describe reality in a more appropriate way. It had to describe order and error in some magical manner. Consequently, probability and statistics were born. But isn't the odds of an event pure chance and therefore chaos? I'm afraid this is a common misconception. Probability is a reflection of the synthesis of law and chaos. Some examples will clarify this. It's an important point. Let us take the case of flipping a coin. In the long run, over an infinite amount of tosses, we know that exactly 50% will be heads, 50% will be tails. This is the statement of law, not chaos. Chaos would be if the outcome were unpredictable. One day heads would occur 10% of the time over a million tosses, let's say. Another day heads would occur 82% of the time, yet another day 64%, etc. Remember, Las Vegas could not exist by chance alone. It is probabilistic law that reigns the craps table and not chaos. That is why they make money. They predict the future. Even insurance companies are built on the faith that statistics are real, can predict their profitable outcomes. So reality is made up of events that have a given probability of occurrence. If the sample is large, then the formulas appear exact. 10,000 tosses of a coin will yield exactly 50% and 50% tails to the expressed degree of accuracy. More precisely, one series of 10,000 tosses may have yielded 50.017% heads, but who cares if this precision is not necessary? Classical physics appeared to work as precise law until the essence of physics, the atom, was explored. It was found that atomic behavior was probabilistic and not deterministic. The micro world operated by the laws of probability and distribution mathematics. It only appeared precise from the larger dimension. Events were found to be guided by law and not determined by it. Probabilistic distributions, which reflected the struggle between law and chaos, were found to be at the basis of reality. Essentially, they describe Ananke at work. The chance universe, where chaos dictates every minute motion, does not exist. Nor does the ordered universe, where repetition and pattern would dictate our every move. It is the conflict between these opposite scenarios that produces the reality that we see. The probabilistic universe is a description of the balance between opposing forces of law and chaos. This is the formula and dynamic of the Ananke. So the study of mathematics deals with the way we can describe events and the way we can manipulate the pure essence of the situation under investigation. Mathematics does not precisely describe reality. It does describe the underlying law which guides the interactions of all things. Mathematics does not exactly predict the future. It does predict the most likely outcome. In essence, it tries to describe Ananke's law. It tries to logically manipulate the resulting equational approximations, thereby predicting the most probabilistic tendencies of events. There can be no doubt that mathematics is built in the faith that logical law guides the universe and not chance. And I think we're going to wrap it up here because we're at 27 minutes, and therefore we will end part 10, and I'll see you next time on part 11, which is the origin of the universe from a philosophic, scientific point of view. Bye-bye.